In this video, we will discuss about introduction to bipolar junction transistor and their configurations, which are useful for all first year engineering students for the subjects like basic electrical and electronics engineering and basic electronics. Now, these are the different types of transistors. In the first generation, which are uses a vacuum tubes, and the size is very large. The second generation, which consists of 3 pin or 4 pins. For laboratory purpose, we normally use a 4 pin or second generation transistors. In third generation, which consists of ICs, in single IC, it may be of 167 transistors. In fourth generation, the size of the IC consists of almost 3510 transistors, 2600 lakhs transistors. The evolution of transistor. This is a size of the size is reduced from first generation to fourth generation. Transistor transfer plus resistor is called transistor. Amplification in transistor is achieved by passing input current signal from a low resistance region to high resistance region. This concept of transfer resistance has gives the name transistor, or simply we can call transistor means transfer of resistor from low resistance to high resistance. Classification of transistors. Transistors are first classified into two types, BJT and FET. BJT means bipolar junction transistor. FET means field effect transistor. Again, BJT is classified into two types, NPN and PNP, whereas FET is classified into JFET and MOSFET. JFET means junction field effect transistor, whereas MOSFET means metal oxide semiconductor field effect transistor. Again, JFET is classified into two types, N channel JFET and P channel JFET, whereas MOSFET is classified into enhancement MOSFET and depletion MOSFET. BJT introduction. A bipolar junction transistor BJT is a three-terminal device in which operation depends upon the interaction of both majority and minority carriers, and hence the name bipolar. The BJT is analogous to vacuum triode and is comparatively smaller in size. It is used in amplifier and oscillatory circuits and as a switch in digital circuits. It has wide applications in computers, satellites, and other modern communication systems. BJT structure. The basic epitaxial planar structure is as shown in figure. Figure B represents an NPN transistor. C represents a PNP transistor. In NPN transistor and PNP transistor, the basic terminals are emitter, collector, and base, which consists of two junctions. One is base collector junction and base emitter junction. BJT is constructed with three doped semiconductor regions separated by two PN junctions, as shown in the epitaxial planar structure. The three regions are called emitter, base, and collector. One type consists of two N regions separated by a P region called NPN, and Other type consists of two p regions separated by an n region called PNP. The term bipolar refers to the use of both holes and electrons as a current carriers in the transistor structure. The p-n junction joining the base region and the emitter region is called base emitter region. The p-n junction joining the base region and collector region is called the base collector region. The base region is lightly doped and very thin compared to the heavily doped emitter and moderately doped collector regions. The three layers semiconductor device consisting of two N and one P type layers in NPN transistor, two P and one N layer of material in PNP transistor. A single PN junction has normally two types of biases, forward bias and reverse bias. In a transistor, there are two PN junctions. Devices have four types of biases: bias mode, emitter base junction, collector base junction. Bias mode is saturation. If emitter base is forward bias and collector base is forward bias, then it is called saturation. Active region. If emitter base is forward bias and collector base is reverse bias, that is called active region. Inverted region. Emitter base junction is reverse bias and collector base junction is forward bias. Cutoff region. If both emitter base junction and collector base junction are reverse bias, then it is called cutoff region. NP and PNP symbols of BJT. The arrow is always drawn on the emitter. The arrow indicates the direction of emitter current. Figure shows for NPN transistor, the arrow direction is from base to emitter, whereas in PNP transistor, the arrow direction is from emitter to base. Now the currents in the transistor are: the current flowing in the emitter is called emitter current, the current flowing in the base is called base current, the current flowing in the collector is called collector current. From these, by applying node analysis, we can directly write emitter current is sum of collector current and base current. Two diode model of BJT. Now we can connect a two diodes back to back. To create an NPN transistor, we need to consider one NP and one PN. Then we have an NPN transistor. If we connect one PN material and one NP material, then we'll have PNP transistor. But in practical, we cannot use two back-to-back diodes. Why? Because the doping concentrations will be changed for NPN as well as for PNP transistors. Emitter is heavily doped, base is lightly doped, collector is moderately doped. Here the figure represents the two diodes connected in back to back with directions of current: emitter current, base current and collector current. Doping levels in transistor. The basic structure of NPN bipolar junction transistor. The figure represents an NPN transistor, and in NPN transistor, emitter is connected at the N-type material, base is connected at the P-type material, and collector is connected at the N-type material. The figure represents free electrons are encircled with black, represents the holes. Base is located at the middle and more thin from the level of collector and emitter. The emitter and collector terminals are made of the same type of semiconductor material, while the other base is of the other type of material. Normally, emitter is heavily doped, base is lightly doped, collector is moderately doped. Working of NPN transistor. The figure represents an NPN transistor. Emitter base junction is forward bias. Collector base junction is reverse bias. Now you can consider the the directions represents the direction of electrons. The direction of electrons, not the direction of current. The direction of current is exactly opposite to the flow of electrons. Now, once a negative terminal at the emitter N is connected to the negative terminal and P is connected to positive terminal, that is given a voltage VEB. Due to that VEB, the negative will repels the electrons in the n-type material, which causes the flow of electrons from n-type material to p-type material. At the same time, collector base junction is reverse bias. Collector terminal is at n-type material and base is at p-type material. Though the electrons in the n-type material are majority carriers in the n-type material are attracted by the positive supply at collector base junction VCB. Due to that one, the electrons are attracted by the positive terminals. The directions represents the direction of flow of electrons. The current flow is exactly opposite to the flow of electrons. It's a working of NPN transistor. Emitter base junction is forward bias and collector base junction is reverse bias. Due to emitter base junction is forward bias, a lot of electrons are from emitter entering the base region. Base is lightly doped with p-type impurity, so the number of holes in the base region is very small. Due to this, electron hole recombination is less. Few electrons, less than 5%, combine with holes to constitute base current IB. The remaining electrons, greater than 95%, cross over into the collector region to constitute collector current IC. Working of PNP transistor. Now, in p-type material, majority carriers are holes. Now, once a p-type material at the emitter side is connected to positive and n-type material at the base is connected to the negative, now which is given as VEB. Due to that, emitter base junction is forward bias. Once emitter base junction is forward bias, the positive repels the holes, the direction of holes from p-type terminal. The directions represents the positive repels the holes, whereas positive attracts the electrons. The directions of electrons flow is represented with arrows. The flow of electrons is opposite to the flow of current direction. Now, once a positive terminal is connected to p-type material, once the emitter base junction is forward bias and collector base junction is reverse bias, due to emitter base junction is forward bias, a lot of holes from emitter entering the base region and electrons from base to emitter region. Base is lightly doped with n-type impurity, So the number of electrons in the base region is very small. Due to this, electron hole recombination is less. Few holes less than 5% combine with electrons to constitute base current IB. Configurations of bipolar transistor. A transistor is a three-terminal device but requires four terminals for connecting it in a circuits. Two terminals for input and two terminals for output. Hence, one of the terminal is made common to the input and output circuit. Common terminal is grounded. First configuration is common base configuration, which has high voltage gain but no current gain. Second one, common emitter configuration, which has both current gain and voltage gain. Common collector configuration, which has a current gain but no voltage gain. So compared to these all three configurations, the best configuration is common emitter configuration. Why? Because it has both voltage gain as well as current gain, which includes that which has high power gain, which is used as an amplifiers. Bipolar junction transistor configurations. Now let us consider an PNP transistor connected in common base, common emitter and common collector configurations. In common base configuration, base is connected for both input as well as output. In common emitter configuration, emitter is connected for input as well as output. In common collector configuration, collector is connected for input as well as for output. Now in practical, we will use NPN transistor compared to PNP transistor. Why? Because in NPN transistor there are more number of electrons. Normally we will call flow of electrons is called current. Due to the high majority charge carriers, we will prefer an NPN transistor compared to PNP transistor. In NPN transistor, the current value will be high. Why? Because there are more number of electrons in the NPN transistor. Common base configuration. Figure represents a common base configuration circuit where base is grounded and is used as common terminal for both input as well as output. Now figure represents an NPN transistor where the base is connected. For NPN transistor, emitter is n-type material, base is p-type material. Now when emitter is connected to negative terminal and base is connected to positive terminal, then input is in forward bias, whereas output side base is p-type material and collector is an n-type material. When n is connected to positive and p is connected to negative, which indicates a collector base junction is in reverse bias condition. Now it is also called as grounded base configuration since the base is grounded. Emitter is used as a input terminal whereas collector is used as an output terminal. Input characteristics of CB configuration. The input characteristics curve drawn between input voltage to input current whereas output voltage is constant. To determine the input characteristics, the collector base voltage VCB is kept constant at 0 and the emitter current IE is increased from 0 by increasing VEB. This is repeated for higher fixed values of VCB. A curve is drawn between emitter current and emitter base voltage at a constant collector base voltage is shown in figure. Now these are the characteristics for different values of VCB from 0 volts, 8 volts and 18 volts. Input characteristics are the characteristics between input voltage versus input current, whereas input voltage is VBE, whereas input current is IE, emitter current. Normally, emitter current is always in milliamperes, collector current is in milliamperes, whereas base current is in microamperes. Why? Because which is only a 5% of emitter current. Early effect, otherwise called as base width modulation. As the collector voltage VCC is made to increase in the reverse bias, the space charge width between collector and base tends to increase, with the result that effective width of the base value decreases. This dependency of the base width on collector to base voltage is known as early effect. Consequences of early effect: there is a less chance of recombinations within the base region. Hence, alpha equals to IC by IE increasing with VCB. Charge gradient is increases within the base, and consequently current of magnetic carrier injected across the emitter junction. For extremely large voltages, effective base width may be reduced to zero, causing voltage breakdown in transistor. This phenomenon is called punch through. Output characteristics of CB configuration. It is defined as the characteristic curve drawn between output voltage to output current, whereas input current is constant. To determine output characteristics, the emitter current IE is kept constant at 0 and the collector current IC is increased from 0 by increasing VCB. This is repeated for higher fixed values of IE. The characteristics are as shown in figure for different emitter currents. By changing emitter current, we will draw the characteristics of VCB versus IC, where collector current IC is in milliamperes, whereas VCB is in volts. From the characteristics, it is seen that for a constant value of IE, IC is independent of VCB and the curves are parallel to the axis of VCB. As the emitter base junction is forward bias, the majority carriers, that is electrons from the emitter region, are injected into the base region. In CB configuration, a variation of the base collector voltage results in a variation of quasi-neutral width of the in the base. The gradient of the magnetic carrier density in the base therefore changes the yielding on increased collector current as the collector base current is increased. This effect is referred to as the early effect. Active region: IE is increased and IC is increased. Base emitter junction is forward bias and collector base junction is reverse bias. Revert to the graph. IC is almost equals to IE. IC is not depends on VCB. Suitable region for transistor working as an amplifier. Saturation region: both base emitter junction and collector base junction is forward bias. Small changes in VCP will cause big difference to IC. The allocation of the region is to the left of the VCB equals to 0 volts. Cutoff region: region below the line IE equals to 0 amperes. In this region, base emitter junction, collector base junction is reverse bias. No current flow at collector, only leakage current. Current amplification factor alpha. It is the ratio of output current, collector current to the input current, emitter current, at a constant collector base voltage VCB is known as current amplification factor alpha. Alpha equals to IC by IE. Expression for collector current. The total collector current consists of that part of emitter current which reaches the collector terminal, that is alpha IE, and the leakage current I leakage. This current is due to the movement of minority carriers across base collector junction on account of it being reverse biased. This is generally much smaller than alpha IE. The total current IC is equals to alpha E plus I leakage. IC equals to alpha E plus ICB naught. Common emitter configuration. In common emitter configuration, the emitter is grounded and is used as the common terminal for both input and output. Figure consists of an NPN transistor. Emitter side N is connected to native terminal and base is connected to positive terminal. Then here base is used as input terminal, whereas collector is the output terminal. This is also called grounded emitter configuration, where the base emitter junction is forward bias and collector emitter junction is reverse bias. Input characteristics of CE configuration. To determine the input characteristics, the collector emitter voltage VCE is kept constant at 0 and base current IB is increased from 0 by increasing VBE. This is repeated for higher fixed values of VCE. A curve is drawn between base current and base emitter voltage at constant collector base voltage. Here the base width decreases, so the curve moves right as VCE increases. The input characteristics of CE configuration is as shown in figure. For different values of VCE 0, 10 and 20 volts, the input characteristics means VBE versus IB. IB is the base current which is in microamperes, where VBE is in volts. Output characteristics of CE configuration. To determine the output characteristics, the base current IB is kept constant at 0 and collector current IC is increased from 0 by increasing VCE. This is repeated for higher fixed values of IB. From the characteristics, it is seen that for a constant value of IB, IC is independent of VCB and the curves are parallel to the axis of VCE. The output characteristics of CE configuration is as shown in figure. The output voltage is VCE and the output current is IC. IC is in milliamperes by considering input current constant. Input current is base current IB in microamperes, 0 microamperes, 20 microamperes, 40, 60 and so on. Active region. Base emitter junction is forward bias. Collector base junction is reverse bias. It can be employed for voltage, current and power amplification. Base emitter junction and collector base junction is forward bias. Thus, the values of IB and IC are too big. The values of VC is very small. Suitable region when the transistor as a logic switch, not, and avoid this region when the transistor as an amplifier. Cutoff region. Region below IB equals to 0 microamperes is to be avoided if an undestroyed output signal is required. Base emitter junction and collector base junction is reverse bias. IB equals to 0. IC is not 0. During this condition, IC is equals to ICE naught, where in this current flow, when base emitter junction is reverse bias. base current amplification factor beta. In common emitter connection, input current is IB and output current is IC. The ratio of change in collector current to change in base current is known as base current amplification factor beta equals to IC by IB. Relationship between alpha and beta. We know that emitter current IE is equals to IB plus IC. By dividing with IC on both sides, IE by IC equals to IB by IC plus IC by IC. Therefore, we know alpha equals to IC by IE and beta equals to IC by IB. Now, by substituting alpha and beta in the above equation, we can obtain 1 by alpha equals to 1 by beta plus 1. Therefore, 1 by alpha equals to 1 plus beta by beta. From that, alpha equals to beta by 1 plus beta. Similarly, from the previous equation, you can write 1 by beta equals to 1 by alpha minus 1. Therefore, 1 by beta equals to 1 minus alpha by alpha. Therefore, beta equals to alpha by 1 minus alpha. Common collector configuration. In common collector configuration, collector is grounded and is used as common terminal for both input and output. It is also called as grounded collector configuration. The figure consists of an NPN transistor. Base is used as input terminal, whereas emitter is used as an output terminal. To determine the input characteristics, the emitter collector voltage VEC is kept constant at 0 and base current IB is increased from 0 by increasing VBC. This is repeated for higher fixed values of VEC. A curve is drawn between base and base collector voltage at a constant base emitter voltage is as shown in figure. Base collector voltage versus base current for different values of VEC. Output characteristics of CC configuration. To determine the output characteristics, the base current IB is kept constant at 0 and emitter current IE is increased from 0 by increasing VEC. This is repeated for higher fixed values of IB. From the characteristics, it is seen that for a constant value of IB, IE is independent of VEC and the curve are parallel to axis of VEC. The output characteristics of CC configuration are as shown in figure. For different values of base current IB, input current, base current is in microamperes. Output characteristics are from VEC versus IE. Current amplification factor gamma. In common collector circuit, the input current is the base current IB and the output current is emitter current IE. Therefore, current amplification factor in the circuit arrangement can be defined as the ratio of change in emitter current to the change in base current. Current amplification factor gamma equals to current amplification factor gamma equals to IE by IB. Comparison of CB, CE and CC configurations. Characteristics: input resistance, common base, low. In common emitter, it is more than common base curve which is of 750 ohms. In common collector which is very high. Output resistance In common base is very high. In common emitter it is high, whereas in common collector it is low. Voltage gain is high in common base configuration, which is about 150. In common emitter configuration, which is very high, about 500. In common collector configuration, which is very low, which is less than 1. Applications of common base configuration are for high frequency applications, whereas for common emitter configuration is for audio frequency applications, whereas common collector is used for impedance matching. Current gain in common base is less than 1, whereas in common emitter it is beta, which is of high value. In common collector, which is appreciable, which is more than beta or beta plus 1. Symbols of thyristor devices: Schottky, diac, SCR, laser, triac, optotriac, SCS, GCS, GTO. SCR means silicon controlled rectifier. Laser means light activated silicon control rectifier. Track means two SCRs connected back to back, whereas diac means two diodes connected back to back. G2 means gate turn off thyristor or gate turn off SCR. These are the different types of thyristor devices. Most common use is of most common used one is SCR, which consisting of terminals like anode, cathode, and gate. Anode, cathode, and gate. Cathode is represented with K, anode is represented with A, and gate is represented with G. Introduction. A thyristor is most important type of power semiconductor devices. They are extensively used in power electronic circuits. They are operated as bistable switches from conducting to conducting state. A thyristor is a four-layer semiconductor PNPN structure where three PN junctions. It has three terminals: anode, cathode, and gate. The word thyristor is coined from thyratron and transistor. It was invented in the year 1957 at Bell Laboratories. Silicon control rectifier. A silicon control rectifier or semiconductor control rectifier is a two-state device used for efficient power control. SCR is the parent member of the thyristor family and is used in high power electronics. A SCR is a four-layer structure, either PNPN or NPNP, that effectively blocks current through two terminals until it is turned on by a small signal at a third terminal. The SCR has two states: a high current low impedance on state and low current high impedance off state. The basic transistor action in a four-layer PNPN structure is analyzed first with only two terminals, and then an input terminal is introduced. SCR construction. An SCR silicon control rectifier is four-layer PNPN device similar to four-layer diode, except the with three terminals: anode, cathode, and gate. The basic structure and the schematic symbol of SCR is as shown in figure. SCR equivalent circuit. Like the four-layer diode operation, the SCR operation can be best be understood by thinking of its internal PNPN structure as two transistor arrangement as shown in figure. This structure is like that 4-layer diode, except for the gate connection. The upper PNP layer acts as a transistor and the lower NPN layer acts as a transistor. Again, notice that the two middle layers are shared. Figure represents the two transistor model of SCR. SCR is in forward bias. There are two different states in which we can examine the SCR in the forward bias condition. The high impedance are forward blocking state. The low impedance are forward conduction state. At a critical peak forward voltage Vp, the SCR switches from the blocking state to the conductance state as shown in figure. A positive voltage places a junction J1 and J3 under forward bias and the center junction J2 under reverse bias. The forward voltage in the blocking state appears across the reverse bias junction J2 as the applied voltage V is increased. The voltage from the anode A to the cathode K as shown in figure is very small after switching to the forward conduction state and all the three junctions are forward bias. The junction J2 switches from reverse bias to forward bias. When the anode voltage is made positive with respect to cathode junction, J1 and J3 are forward bias and junction J2 is reverse bias. With the anode to cathode voltage being small, only leakage current flows through the device. The SCR is then said to be in the forward blocking state. If VAK is further increased to a large value, the reverse biased junction will break down due to avalanche effect resulting in the large current through the device. The voltage at which the phenomena occurs is called forward breakdown voltage VB0. Once the SCR is switched on, the voltage drop across it is very small, typically 1 to 1.5 volts. SCR in reverse bias. In the reverse blocking state, the junctions J1 and J3 are reverse biased and junction J2 is forward biased. The supply of electrons and holes to the junction J2 is restricted and due to the thermal generation of electron-hole pairs near junctions J1 and J2, the device current is small saturation current. In the reverse blocking condition, the current remains small until avalanche breakdown occurs at a large reverse bias of the several thousand volts. An SCR PNPN structure is equivalent to one PNP transistor and one NPN transistor sharing the same common terminals. VA characteristics of SCR for zero gate current where there is no gate voltage. No, in there are three states: forward conduction mode, forward blocking region, and reverse blocking region. In forward blocking region, the junction J2 is in reverse bias, whereas in forward conduction state, the junction J2 is breaks and J2 becomes a forward bias. When the gate voltage increases from 0 voltage, junction J2 becomes forward bias for lesser breakdown voltage. Hence, all the junctions are forward bias. With the higher gate voltages, forward breakdown voltage reduces as shown in figure. Figure represents the circuit represents a SCR with a gate pulse. The characteristics are as shown in figure. For higher gate voltage, the breakdown voltage will be reduced. Figure represents a latching current IL and holding current IH. Latching current of a SCR is defined as the minimum value of anode current above which the SCR is in on condition, even the gate supply is removed. Associated with turn on and is usually greater than holding current. Holding current of an SCR is defined as the maximum value of anode current below which the SCR is in off condition and is associated with turn off of SCR. Applications of SCR. It is used in motor speed control, heater control, phase control, battery chargers, inverters, static switches, relay control, rectifier power supplies. Thank you for watching. Please share and subscribe if you like.